In this section, we're going to take the core tensor primitives that we learned about in the last segment and build an encrypted database. Now, the reason we're interested in doing this is that just to show the general nature of encrypted computation, it can be based off of tensor representations. And also as a bit of a simple and more creative exercise before we jump into deep learning. So the first thing that we're going to do is we're going to take individual strings, so it's going to be a key value database, string representations, and we're going to convert them into these tensor operations and then show how these tensor operations can actually be used to perform queries. The big feature of this encrypted database is that it makes it so that the database owner can't see any of the data because the data is sort of encrypted while it's in the database. It can't see what people are querying for or what the results of the query actually return, right? So that the database owners end up being totally oblivious to what's going in and what's coming out of the database. However, because all the values are encrypted using secure MPC, you can have a group of database owners, sort of multiple individuals that have sort of joint ownership and joint governance over people's ability to sort of use and query this information. So let's begin. The first thing we need to do is actually come up with numerical representations for strings. And we're going to do two different ones. So there's kind of two canonical ways you can represent strings as numbers. One, you can use a one-hot representation, or you can use integer representations where each integer represents a different character or word. Now we're going to focus on character representations, right? And then we're going to do both. For the sake of demonstration, we're going to do both one-hot representations and integer-based representations, so you kind of get a full intuition for how these can be represented. So first, we need to choose what subset of characters we want to support in our database. So the first thing we're going to do here, we're going to create a couple lookup tables that map characters to integers, and then we'll use that to create both representations. We have to basically say, we have to correspond letters with numbers at some point, so that's sort of the best place to start. So let's import string, and we're going to do two lookup tables, as is common in NLP. One that goes from character to integer, and the other one that goes from integer to character. And for what do we want to support? So we want to support space. That's kind of important because people encode space all the time. We want to encode lowercase ASCII characters, and we want to encode numbers. And we want to encode, let's say, punctuation. Cool. So we're basically everything that you would use kind of on an everyday basis, with the exception of uppercase letters. So we're just going to lowercase everything before people put it in the database or before they perform queries. Cool. So let's put this into our lookup tables. So we do this, I, C in enumerate. So if you're not familiar with Python's enumerate function, it's basically a for loop, but it gives I, which is telling you what index you're at. So I guess I should probably name this char. Char to int, char equals I, int to char, I equals char. Cool. Char to int to char. There you go. And now we can map between letters and numbers. However, this is not yet sufficient, right? So we need to actually be using torch tensors so that we can do encrypted computation using the tools that we learned about in the last segment. So how are we going to convert them into tensors? Well, there's two different ways. One, we can use one-hot representations, or we can actually encode these raw integer values as tensors. So encoding these values as sort of tensors, that seems like a little bit easier. So let's start there. So we'll call this string to values, and it'll take the string input. And then also, because we want all the tensors returned from this method to be the same length so that we can concatenate them into one large tensor, let's go ahead and set what a max length would be. We'll set it to be 8. So this will be our sort of API. And for the sake of building this, we'll work with an example that's hello and max length. So we'll just keep that at 8. Okay, so first thing, because we're not supporting lowercase numbers, we need to strip them out. Okay, so stir input equals stir input. So trim any strings that are too long and convert them to lowercase where they are uppercase. Cool. And now the next thing we need to do is if we get a string that is too short, so in this case, it's obviously less than 8 characters, then we need to pad it with periods. We could use any special character, but in this particular case, we're going to use periods. So if len stir input is less than max len, stir input equals stir input plus period times max len minus len stir input. And if you're not familiar, whenever you take a Python character and you multiply it times something, it just repeats it over and over again. Cool. So it's concatenating repeated periods to make it so that stir input, the length of stir input, is always 8. If it's too long, we trim it. If it's too short, we pad it. Cool. So now all of them are the same length, which means we can pack multiple of these representations into a single tensor, which will be really ideal later. Cool. So now all that's left to do is to actually create the tensor of character integers, character indexes, right? Actually, yeah, maybe call this index. That'd be a better. Yeah, that just makes more sense. Perfect. Okay, so for char vectors equals list. No, values equals list. For char and stir input, values that append. Char to int, char. So values, so HELLO, period, period, period. And we'll just convert this into a tensor of longs. Beautiful. Might need that in a minute. Okay. Return. Beautiful. Perfect. And if it's too long, it just truncates it, which is great. Okay, so we have string to values, but we also mentioned there was another way that we could potentially represent strings, and that was representing them as one-hot vectors. Now, if you're not sure what a one-hot vector is, it's literally just a vector of like 0, 0, 0, 0, 0, 0, 0, 0, where one of these zeros is a 1. And it's the placement of this 1 that actually indicates what this is trying to encode, right? So in this case, there's 1, 2, 3, 4, 5, 6, 7 things that could be encoded here, and it's saying at this position is the fourth, whatever the fourth thing in the vocabulary is, right? So in our particular case, so let's create first a handy function for generating one-hot vectors. So we're going to start with a vector of zeros, and then we're going to say, okay, at whatever this index position is, we're going to set it to 1. So, and then return vect. Cool. So 1 hot, 3, 5, 0, 1, 2, 3 is a 1. The rest of them are 0. Perfect. So now how can we represent characters as one-hot vectors? Well, each character, so if I go 1 hot, so char to index p, I'll just pick one character randomly, and then this would be the length of index to char, right? And what this is this is a vector that is, of length, however many characters there are, 69 characters. So there's 69 different characters we could select in this vector, and we have selected the one corresponding to p's index, right? So this p right here. Cool. So now all we need to do to encode a string as a series of one-hot vectors is just do this multiple times and concatenate these tensors together. So let's do that. So we can copy most of this pre-processing stuff. String to one hot matrix. Okay. But instead of doing this, we are going to say char vectors equals list, and then for char in string input, char, one hot equals char v equals hot, and then yeah, I think that works. And then we want to add an extra dimension, which will make it easy for us to concatenate in a second. And then we're going to return these vectors concatenated together, but along the first dimension. And so what does this yield us? Oh, I forgot one step. So this yields us a matrix with 8 rows representing 8 characters and 69 columns corresponding to the 69 possible values that each character could take on, right? So in this particular case, this number 1 corresponds to the H, this number 1 to the E, L is the other in the same position, and then O is over here, and then we just have different periods after that. So that is how this is encoded. Yeah, so now we have our matrix. So let's take, we have these 2 different ways of encoding information, and we're going to build our database to be a key value store of strings, right? So the way that I would like to store these things in the database is to store our keys using our sort of one-hot encoding, but our values using our string to one-hot matrix. And let me show you why. So let's say this clever thing we can do. So with the one-hot matrix, so we can say this is hello. So string A and string B. Now let's say we wanted to check and see if these strings were identical. Okay. Well, we have tensor representations here, so we can go string A times string B, right? And then what does this do? This means let's use ones that aren't identical. So like A, B, C, D, E, okay, F, G, H, I, J. Okay. What's going to be the sum of this multiplication? 0. Why? Because when we multiplied these together, only place values where both strings had a 1 in the same location would multiply to put a 1 in the result, right? So this is basically saying there are 0 characters in common. So if I said space H1 1 this has 1 letter in common, right? E 2 letters in common, L 3 letters in common, L 4 letters in common, right? Because basically this is just a one-hot vector, and if we multiply element-wise 2 vectors together that are all 1s and 0s, it's going to zero out any locations where they don't have a 1 in the same place. And for our purposes, when string A matrix and string B matrix have a 1 in the same place, it means that they have a character in the same location. And that is exactly what we are interested in being able to check for, right? So when we want to do sort of key matching, this ends up being quite a useful tool, because it means that we can use this kind of multiplication to be able to tell whether or not a given key is a perfect match with a different with a particular query, right? And this allows us to do sort of a key value lookup using sort of this multiplication tool, which is quite nice. So another way we could potentially do this is we could do sum along the 0 dimension, right? And this looks at sort of how many ways these are sum over how many characters are sort of overlapping. So in this case, 2 L's, 1 E, and 1 H. We do it along the 1 dimension, then we see how many of the characters actually overlap as a matter of placement, right? So this one overlaps, this one overlaps, this one overlaps, this one overlaps, and these ones don't, right? Because the last 4 were actually, these are 1s, whereas this is 0, and then it had the padded token, right? So there's also other operations we can do here that can kind of tell whether or not we have perfect matching. And now the other interesting thing is that Now that we've done it this way, we don't care about whether they just match individual characters. We mostly care about whether they match completely, whether all of them match, right? So in this particular case, some of them match, not all of them. So like let's see. So if we called this sort of, it's kind of a partial query vector, then we still actually need to check. So this is the sort of whether the first one matches. We need to check to see whether all of them match. We can do this by just multiplying all these values together. And if there's a 0 anywhere, then the result of this will be 0. But if there are 1s in all these locations, then the product of all of these numbers will also be a 1. And that would mean that these two strings are exactly identical. So, and again, this is still just using multiplication. So for I in range x equals x times vect I. See, when we got to the zeros, this turned into, x started turning into a 0. Actually, we can trim one off here because we already have this here. Yeah. Perfect. So we're getting close. So now this x is strings, so key match equals x. So this is a Boolean value, a 1, 0 value that represents whether or not these match. So if I were to say, so right now they don't, right? So key match equals 0. If I were to set these to be the same thing, key match equals 1. Perfect. So now we've used exclusively multiplication, right, to be able to encode a Boolean bit, right, a true-false bit that determines whether or not these two keys match. And this is super useful for being able to again, we're encoding this database as Boolean logic. So the fact that we've sort of gotten this incremental piece where we can do string comparison using just multiplication means that in MPC, in an encrypted space, we can also do string comparison using just encrypted multiplication, right? So we're going to keep sort of building the different components of this database while only using these sort of base core primitives operating over kind of Boolean and integer values. Okay, so now let's talk about how we want to save things into the database. So the database, it's going to need keys, and it's going to need values, right? And so let's create a dummy key and value. So let's say keys.append, key, and then values.append value. Okay, that's interesting. But again, we can't store these as strings, so we need to store them as numerical representations. Now, we already showed that we can do key comparisons to see, whether two keys are the same or whether a query is the same as a key, right? So now let's actually modify this to do this kind of string to one hot matrix, right? So keys.append string to one hot matrix our key. Now, how should we encode our values? We could totally encode our values as a string to one hot matrix, but I would like to do it instead as using this other one, using this sort of string to values, which is actually a much smaller representation. Like it's quite a bit more concise. So we'll do strings and values. So now we have keys and we have values. Okay, well let's do a couple of these. Key 1, value 1. Key 2, value 2. So now we've got a couple keys, got a couple values. Perfect. We got 1 and 2, so they're slightly different representations. Okay, great. So now we've got the ability to sort of do string comparison. And we've got some basic keys and values. So now, how can we perform a query against this sort of pseudo database? So a query to a key value store first needs to compute whether the query matches any of the other keys. So first things first, we want to say query. Let's say our query string equals key 1. So that's what we're going to look for. Okay. Now key 1, we first need to convert it into the correct representation, which is a string to one-hot matrix. So query matrix equals query string. And again, this is not having to do with cryptography. This is just about converting string logic into Boolean circuit logic so that we can do it with our encrypted hardware in a minute. So query matrix. So this is our query matrix. And now, how do we actually perform the query? The way we perform the query is we just iterate over all the keys and figure out whether any of them match. So for, let's see, so def query. No, we won't worry about making it a function yet. But so let's say for key in keys, query matrix. Let's see, key match equals query matrix. Strings equal. Should call this string match probably. Strings equal key and query matrix. Okay, now let's check it for all the keys. Actually, it's key matches. I guess probably a better way to do that. Okay. Key matches, not keys matches. Okay, so look. Now with key 1, we have, this returns a tensor with a 1 in it, which is a true, and this and 1 with a false. So we know that this is actually matching the first key, right? So now if we were to check, if we were to change this to key 2, okay, key does not match. Now we are actually quite close to being able to get our final result. So the usefulness of this key matches is that then we can use this to index into the values and decide which value we want to return. And we're going to do this in a way that I think is actually quite clever. So values are encoded using these integers. So the thing that we can do is we can actually mask out all the values that don't have matching keys. Meaning if I took values 0 and multiplied it times key matches 0, they all turn into zeros. Why? Because key matches 0 wasn't a match. Or if I do values 1 times key matches 1, I get to maintain all of them. And the interesting thing is that if I only have a key match with one value, so under the assumption that all keys are unique, then I can sum across these individual entries, right? So whether there's a sort of a value match, right? And then I will get the resulting value. So if I go value match equals 0, 0, and I go for I in range lang values minus 1 value match plus equals values I plus 1 times key matches I plus 1, then the result will be the numerical representation of the matching values, right? So if you look at result here, because it's adding up, it's basically adding up all the values, but before it does that, it masks out the ones that don't have matching keys, right? So in this case, the result right now, see how this is 29. Now if I flip to key 1, this is now 28, right? Because it indexes into the sort of other entry. And now the question is, okay, so it's useful that we returned the right tensor, but how can we get a tensor that, you know, is strings instead of numbers, so we can actually get the string value back? And for this, we need basically just one more sort of simple helper function. And that simple helper function is going to reverse the string to values encoding that we did. So we'll go def values to string. input values. And so basically this means that we can, so if we have an empty string, and we go for value in input values, concatenate to our string int to char int value. Whoop. Return s. And now this allows us to go close. Value 1 dot dot. Perfect. And now if we just say, replace periods with space just so it looks nicer. Actually, we could replace periods with nothing if we wanted to. Then we have the result from our database. So there you go. Def query. And this query operates using exclusively addition and multiplication. So if I go query key 1, whoops. Oh, query value 1, key 2, oh. Value 2. All right, there we go. Okay, so how do we actually pack this into kind of more of a database? So we sort of got like a loose collection of functions here, but it'd be nice if we actually had the ability to sort of have a a class that was like decentralized database. So like let's make one, or we could say encrypted database. Yeah, you can choose what you want to call your database yourself. So we have self. I think we should store. So we have several values here that we're really keeping. So we have max key length, which was, I believe, both of them are 8 at the moment. Both of them are 8. So self.max key equals 8. Self.max file length equals 8. And then we've got this query logic, which is quite useful. Oh, we need to encode sort of keys. Where were keys? We'll just encode these values here real quick. So we should do self dot and self dot self dot self dot. Cool. And so what's the next thing we want to do? So we've got, this is more of a convenience function. It's not really object oriented, so we'll keep that in its own section. Okay. Now I've got the query. And we just got to make sure that we use self.keys. I believe, oh, and self.values. Beautiful. So now if we have db equals encrypted db, db.query, value 2, value 1. Perfect. Okay. Now, basically just need to have another function that says add entry. So we don't have to sort of pre-populate these. So we just go string key value. Oh, self key value. And it's quite simple logic, really. Just key value. So now we can go encrypted db, add entry, key 1, value 1. We'll just do a few. Interesting. So what this key error tells us is that our int to char is missing something. So what could it possibly be missing? So the thing we want to do here is on so basically it was in values to string. So we'll print the result. So it looks like something caused it to be padding with 100s instead of with what we wanted it to be. So let's just make sure that this is all initialized correctly. Okay. Int char goes up to 68. Char to int. Looks like it doesn't really go over 68 either. That makes it quite unclear to me. Oh, it means we probably had... Since these are all divisible by 2, I would bet good money that means that we accidentally had duplicate keys. Oh, and of course, we did, because we were putting them in twice. There you go. So, value 1. Now, we could put in another check here to actually check to make sure that, it sort of returns that, it sort of ensures that it only has unique keys when you add them, but that's not necessarily something we have to worry about. If you're going to build a real database, feel free to worry about things like that. But for this particular demo, I think I'm not going to really worry about that. So now, this is pretty cool. This is a Boolean database, quite convenient, but this is not exactly what we originally set out to do. What we originally set out to do was build an encrypted database, which is exactly, why it's called Encrypted DB. But all the operations that we've done so far are addition and multiplication based using torch tensors, which means that we can actually cause all these encodings to be using secure MPC. So actually the first thing we need to do is have a series of owners. And what those owners can do is those are just basically owners of the database, right? So these will be people, right? Or I guess virtual workers. Self.owners equals owners. And now I can go key equals key.share owners. And this is what's going to allow us to say self.owners. So it's going to take the vector representation of the key and share it amongst the owners. And of course, we do the same thing for value. And now, when we add entries to our database, keys, db.values. So just checking to make sure they're all in there. Perfect. Cool. So we got 4 keys and 4 values. Now the one thing that we still have yet to do though is when we query something, it means we also need to share that. And before we do this fancy sort of decoding, we need the result to be decrypted. And that should be it, I think. Oh, pretty close. Oh, self.owners. Getting close. So it looks like we have an error in our key match logic for comparing two operations. So let's just introspect this a little bit. Oh, I know what the issue is. We didn't pass in any owners. Boom, there you go. So now we have a database that can operate over encrypted values. And not only that, but the database is actually has shared ownership across these three different individuals, which means that these three individuals have joint governance over the encrypted data that's in between them. However, people can't actually query it without revealing what they're querying to any of these shareholders. So I hope you'd enjoyed this interesting demo, and that you sort of are inspired that these basic building blocks can make it so that we can build encrypted data structures and encrypted programs that have this kind of decentralized governance, right? So that maybe just a slightly different demo here would be to like say, okay, what if we have a phone registry system, and then I say Bob, and then I guess I have to set my value or max val length to be say 256, and I'd have to set max length equals self dot. Oh, this is key, so that's different. All right, and there you go. So yeah, in essence here, we're able to store strings of somewhat arbitrary value. And we can do maybe a simple phone registry like this, or we can do a key value store where the key returns some big JSON value. It's an arbitrary key value database. This could do a distributed ledger, right? They kept track of bank balances. It's an incredibly flexible sort of simple key value store, and really any computation you want to be able to do can be done using Boolean circuitry. And with these underlying primitives, it's possible to do encrypted version of Boolean circuitry, which is quite exciting. All right, so moving on from this, we're actually going to focus a little more on actually doing things with deep learning. In the next section, we're going to talk about how to encrypt a neural network and a data set and run a prediction while they're encrypted. So I'll see you then. Bye.